any proportional similarity or correspondence in the arrangement of parts of an object or pattern. In simpler terms, it's when something looks the same after a transformation, such as flipping, rotating, or translating. The first type of symmetry is reflection symmetry or mirror symmetry. This symmetry occurs when one half of an object or design is a mirror image of the another. You can divide the shape or object along a line, the line of symmetry, and both halves will match perfectly. For example, is the butterfly wings. The two wings are mirror images of each other when divided down the middle. The second one is the cat's face. If you draw a vertical line down the middle, the left and right side of the face are nearly mirror images of each other. The second type is rotational symmetry or radial symmetry. This exists when an object looks the same after being rotated less than a full circle around a central point. The object can be rotated by certain angles like 90 degrees or 180 degrees and still look the same. The first example is a wheel. A wheel like the one on a bicycle or a car has rotational symmetry. When you rotate the wheel, it looks the same at certain intervals. The second one is a fan blade. A fan's blade have rotational symmetry, often looking the same when you rotate the fan by 120 degrees, 180 or 360 degrees. The third type is translation symmetry. This occurs when an object or design can be shifted in space, moved along a straight line in a particular direction without changing its appearance. There is no rotation or refraction involved. The examples are grass block pavers or turf block pavers. In these pavers, the pattern of blocks repeats consistently, either horizontally or vertically. This repetition of pattern without any change in its structure or orientation demonstrates translation symmetry. The second is tiled floor. A floor with a repeating tile pattern such as squares or rectangles exhibits translation symmetry. If you slide the entire pattern across the floor, it remains unchanged.
Spiral. So what is spiral? Spiral is a perfect curve that starts from a central point and moves outward or inward continuously in circular patterns. First example of spiral is mosquito coil. Mosquito coil is an example of spiral because it follows continuous curved path that starts from the center and expand outward. Second example of spiral is millipede. Millipede is an example of spiral in nature because of its natural defense mechanism. When treated, millipede curl their bodies into a spiral or coil, forming a protective circle. Bubbles and foams. Bubbles and foams are small pockets of gas trapped within solid or liquid structure. First example of bubble and foams is fountain bubble. It considered as an examples of bubbles and foam because it involves formation of gas bubbles that trap in water, which is essential what makes up foam. Second example of bubbles and foams, soap bubble, are a perfect and easy to understand example of both bubbles and foams because they show how air can be trapped inside a liquid film, forming bubbles, and how many bubbles can cluster together to form a foam.
So hi guys, for today I will be discussing to you the Mender pattern and its example. So Menders tend to have a consistent and repeating pattern of curves and bends. The curves are smooth and flowing, resembling the shape of sine wave. Mender patterns are not static. They evolve over time as the forces of erosion and deposition continue to shape the environment. So here's the example of Mendel's pattern. So this picture, I took this in Vito Barel, Cebu. The picture shows a winding mountain road with sharp curves. Using the Mendel's mat pattern, we can analyze the curves geometrically, consider the road slope, and understand how perspective affects our view. The curves are essential for navigating the terrain, and their design involves mathematical principles. While we can calculate exact numbers without measurements, we can appreciate how math is applied in road constructions and navigations. So here's another example of Mendel's pattern. So this picture, I took this in my mom's garden. The eggplant leaf in the image displays a branching, meandering, net-like vein patterns due to the need for efficient transport of water and nutrients throughout the leaf, structural support, developmental constraints during the leaf growth, and space optimization. This pattern, characterized by its winding and turning course, resembling a reverse meanders, ensures all parts of the leaf are serviced by the vascular system. The meandering nature specifically highlights how the veins curve and loop, effectively covering the leaf surface without strict straight lines, maximizing contact area and resource distribution within the given space. Mender patterns are a fascinating example of how natural forces can create beautiful and complex design in the world around us.
Waves. A wave is a physical phenomenon characterized by its frequency, wavelength, and amplitude. In general, waves transfer energy from the one location to another. The example of dropping a coin into water illustrates wave patterns in nature. When the coin hits the surface, it disturbs the water, creating concentrated circular waves that move outward. These demonstrate how energy is transferred to a medium of water without the actual movement of the medium itself. The ripples are an example of transverse waves, similar to how sound waves, light waves, and seismic waves propagate in different environments. The simple experiment reflects broader natural wave phenomena such as ocean waves, sound waves, and even electromagnetic waves. Affine transformations. The affine transformations is a linear mapping method that preserves points, straight lines, and planes. The process involved in affine transformations are rotations, reflections, and scaling. An example of affine transformation is the snake plant or Sansevieria trifasciata. This snake plant can be found in our garden. The snake plant has points and lines, it grows rotationally, and it leaves reflections with each other. The snake plant or the Sansevieria trifasciata exhibit a natural affine transformation pattern in its leaf growth. This means that as new leaves grow, they maintain a similar shape and pattern but may scale, rotate, or shear slightly relative to older leaves. This transformation follows self-similarity, a key feature of fractal-like growth in nature. The venation pattern and variegation or wavy green-yellow stripes also follow an affine transformation, affering stretch or compress while maintaining their fundamental structure. This pattern helps the plant optimize light capture and enhance their aesthetic appeal.
Of tessellations is a brick-style wallpaper. Brick-style wallpaper is an example of tessellations because it features a repeated patterns that covers an entire surface without any gaps or overlaps. Tessellations in a mathematical sense refers to the arrangement of shapes that fits together perfectly to fill a plane. In the case of brick-style wallpaper, the design uses geometric shapes or motifs that interlock in a way that the entire surface area is filled with no empty spaces. making it a visual example of tessellations. This is similar to how tiles are arranged on a floor or a wall to create a seamless pattern. Thank you.
Stripes and spots are both adaptive patterns that help animals camouflage, communication, and protection. They illustrate the diverse way in which nature uses patterns for survival and interaction. Stripes and spots can be seen in various places across the natural world, especially in animals. Stripes and spots are a widespread feature across plants and natural phenomena, providing various functions. These patterns are everywhere in nature, from the skies and oceans to forests and deserts. Many natural things incorporated patterns, spots, and stripes in their development and hypothesize that there might be a mathematical model that could connect and explain these patterns.
Fractals. Fractals is a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. So I will show you an example of fractals. So the first example of fractals is a leaf. So if you look closely at the leaf, you will see a bunch of tiny veins branch out. The branching pattern repeats at different scales, or also known as self-similarity. And this branching is iterate, creating a complex structure, making it the best example of fractal pattern. So here's another example showing fractal pattern found in nature. Tree branches. So as you can see, just like the first example I showed to you, the branching pattern of this tree repeats at different scales. The branches divided into smaller branches, which also divide into smaller ones, and so on, making it the best example of fractal patterns found in nature. Fibonacci sequence. Fibonacci sequence is the series of numbers in which each number is the sum of the two preceding numbers. So Fibonacci sequence usually starts from 0 and 1. So Fibonacci sequence is given by 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. So here's an example of Fibonacci sequence. The palm. So we can see that there is one palm, and our palm has 5 fingers, and each fingers has the 3 lines on it. 1, 2, 3. So the Fibonacci sequence can be seen in the arrangement of our fingers on our palm. 1 palm, 5 fingers, and the 3 lines on our finger.
So here's another example of Fibonacci. Tornera of Olmifolia is an example of the Fibonacci sequence because its flower exhibits a petal count and a growth pattern that aligns with Fibonacci numbers. The plant's overall arrangement and design are guided by the optimization principles found in the nature, which often manifest through the Fibonacci sequence.
Fracture and cracks can be observed in various materials and structures, including buildings, bridges, machinery, and even human bones. Understanding where fractures and cracks appear and their causes is essential for ensuring safety and durability in different fields such as engineering, construction, and medicine. Fractures and cracks can be seen in multiple areas, such as buildings and infrastructure, Cracks often appear in concrete structure due to thermal expansion, shrinkage, or excessive load. Bridges, roads, and dams are also prone to fractures due to environmental stress and aging. Glass and ceramics. Fracture in glass, windows, screens, and ceramic materials typically occur due to impact or thermal stress.